Okay, hello everybody. Let's go ahead and talk about the fundamental theorem of calculus. Now let's go ahead and take a look at what we had from before so that we can talk about what this does. We said we had two types of integration. We had definite integration, which is the integral from a to b f of x d of x. That gave us a number which represented an area. And we also had indefinite integration, which is the integral of f of x d of x, which is equal to capital F of x plus c. And we said that that was going to be a family of functions. Now, what the fundamental theorem of calculus will do, it will actually combine those two concepts and the skills to be able to actually determine the definite integral for any particular function that you have. So let's go ahead and take a look at what it looks like. This is what it looks like. It says that if you have a definite integral, the integral from a to b of f of x d of x, I'm going to first use my rules of anti-differentiation to come out with a capital F of x. And then what I'm going to do is notice that I have here a bar with the same upper and lower limits of integration. I'm going to evaluate the antiderivative function at b and at a, and I'm going to subtract it to come out with a number. And that number, of course, will be the area which represents this definite integral. So let's take a look at an example. Say, for example, that we have f of x is equal to x squared plus 1 on the interval, closed interval 1 to 2. So I went ahead and substituted 1 into here and I came up with 2. Substituted 2 here and came up with 5. I know that this is a parabola that's just been shifted up 1, so it looks something like that. But the area that we're dealing with, of course, remember, is going to be bounded by x is equal to 1 and x is equal to 2, which is here and here. It is also going to be bounded by the function itself, as well as the x-axis. So the area that we were trying to calculate with this definite integral is this part over here, which is in green. Now before, what we dealt with are things that are shapes, geometrical shapes created by the function that we could actually calculate because we had formulas for. But if you go ahead and you take a look at this situation here, this is a curve. And so we have no geometric formula to actually be able to come up with the exact area that is shaded here in green. So what do? We have to use the process of anti-differentiation, evaluate the antiderivative, and use basically the fundamental theorem of calculus to actually come up with a number which represents the exact value of that area. So let's go ahead and take a look at how we do this. So if we go ahead and take a look at the antiderivative of x squared plus 1. So what I'm going to use then is the antiderivative rule for the power rule, and I come out, I add 1 to that, multiply it by its reciprocal, so that's 1/3 x to the third, plus, and this is just the value of 1, so the derivative, or sorry, the antiderivative of that would just be x. Okay, so now if we want to just go ahead and check to make sure that this really is the antiderivative of that, if I take the derivative of this, I'd better come out with that. Let's just do that just to be on the safe side. If I take the derivative of 1/3 x to the third, then I take the derivative, that's going to be 3, multiply that, that's going to cancel this x squared, and the derivative of x is going to be 1. Excuse me. So I know that this antiderivative is correct. Notice that I'm going to now then evaluate it from 1 to 2. And I substitute the values of 2 into this antiderivative here. And I come up with 1/3, 2 to the third plus 2, which is that part. And then I'm going to subtract the same antiderivative function, evaluate it at 1. And I come out with 1/3. 1 to the third plus 1. So now I can go ahead and simplify this even further, and I get 8/3 plus 2 minus 1/3 plus 1. So what that will give me then is 8/3 minus 1/3 is just going to be 7/3. 2 minus 1 is just going to give me 1. And if I add that together, I come up with 10/3. So 10/3 is actually what the area is under this curve, bounded by the two sides and the x-axis. And there you go. That's how you can use the fundamental theorem of calculus to evaluate any indefinite integral using your rules for anti-differentiation. Okay, lastly, and again, we'll take a look at some more examples in class. But lastly, here's a couple of questions for you, true or false and why. If I was to go ahead and take the integral, the definite integral, from a to a of f of x d of x, is that equal to 0? If I was to go ahead and take the derivative, the indefinite integral, the definite integral, from a to b of f of x d of x, is that actually going to be the same thing as the opposite of the integral from b to a of f of x d of x? Now, actually, instead of saying whether these are true or false, both of these are true. The question is why? And let's see if you can think about that, and we'll look at it later. Okay? So, there you go. Oh, one last thing. Make sure that f of x is continuous on the interval through which you're integrating. Okay? So, in this case over here, f of x has to be continuous anywhere in between those values. Okay, and that's what the fundamental theorem of calculus will do for you. It will go ahead and be able to give you the value of the area using your rules of anti-differentiation. Okay, see you next time. Bye-bye.